Photosynthesis is a process by which plants and other organisms take light energy and convert it into chemical energy in the form of carbohydrates. Okay? Plants take in CO2, convert it into sugar, say glucose, or if it's a polymer, then say starch, store it. Other heterotrophs eat these autotrophs and then obtain that energy. Basically, sun is the primary source of energy, and these heterotrophs, they obtain their energy from autotrophs. Now, this entire reaction, CO2 plus water, will give you glucose and oxygen and few water molecules. In this entire reaction, your carbon dioxide is being reduced to glucose and your water is being oxidized to oxygen, right? What is the process of oxidation and reduction? In terms of electrons, loss of electrons is oxidation, gain of electrons is reduction. In terms of hydrogen ions, again the same thing, loss of hydrogen ions is oxidation, gain of hydrogen ions is reduction. With carbon dioxide, you are adding hydrogen atoms, so CO2 is getting reduced. Whereas for water, you are taking out hydrogen ions, and what you are left with is oxygen. So it is a process of oxidation. Okay. This is nothing but just 1 second. So you can see this is the process, very simplified. Not the R level thing. This is the actual summary of photosynthesis. Sunlight, primary source. Chlorophyll is the pigment molecule which picks up sunlight, the energy of the sunlight. You see, water is showing 3 arrows. That means water is being split, okay, into H plus ions, OH minus ions, and energy is given out. The OH minus ions form oxygen, which is released. You can see the perforation showing the light and dark reaction. Now, what is light reaction? Light reaction essentially needs sunlight. Cannot do without sunlight. Dark reaction does not mean it occurs at night. It only means that sunlight is not a part of the reaction taking place. ADP is converted to ATP. Okay, this is occurring in the light reaction part. ATP and NADPH2 are getting generated in the light reaction. They are being utilized in the dark reaction. They are called as assimilatory part. Okay, so they are produced in the light reaction part of it, consumed in the dark reaction part of it. In the dark reaction, fixation of CO2 occurs. That is the main process in the dark reaction, taken up by RADP or RADP, DP, that is ribulose 1,5, bisphosphate to diphosphate, phosphoglyceric acid converted to phosphoglyceraldehyde, and the further processes converted into sugars and other products.
Can you please this RADP is
ribulose 1,5-bisphosphate. These HMP shunt pathway comes where it's HMP shunt pathway is not a process, a part of photosynthesis, right?
Precursor molecule is ribose is combined, ribulose pathway is combined with CO2. Precursor molecule came from where?
It's a regeneration cycle. When I cover dark reaction, you will see that this combines with CO2 to form a 6 carbon. Okay, it will come later. I'll just tell you to clear your doubt. 5 carbon RADP combines with 6 carbon CO2 to form a 6 carbon unstable intermediate, which is immediately broken down to 2 molecules of 3 carbon phosphoglyceric acid converted to glyceraldehyde, sugar, and from this glyceraldehyde you can again regenerate RADP. I hope you remember the reactions. If you can recollect something, glyceraldehyde, dihydroxyacetone phosphate are interconvertible. They are taken out, and there is a series of reactions in which 3 carbon and 5 carbon can combine to form cerohexylose, 7 carbon compound, erythrose, xylulose, all these. Yes, see, There are many intermediates which are common between photosynthesis and your respiration. HMP shunt comes as a part of respiration, right? Not a part of photosynthesis. There are many interconvertible intermediates. They jump from here to there to here. Okay? What is dividing them is the compartmentalization, right? That's why you have a different chloroplast for that. You have mitochondria for that. Some of these reactions take place in the stroma of the chloroplast, right? The other reactions take place in the matrix, those invaginations of the matrix cristae and the F1 particles. That is physical compartmentalization, keeping them separate. Okay, otherwise what would happen? It would have been a complete chaos. What you're saying is right. There are many intermediates. Not only this RUDP, there are many intermediates. Phosphoglyceric acid, 3-phosphoglyceraldehyde. What are those? They are glycolysis intermediates, right? What happens in glycolysis? Glucose, glucose 6, fructose 6, fructose 1,6 bisphosphate, glyceraldehyde 3-phosphate. Next is 1,3-bisphosphoglycerate, phosphoglyceric acid. There are many intermediates which are common. Okay, what differentiates them is the physical compartmentalization. Okay, so this will study how RUDP is regenerated again when we study the dark reactions. Okay, the light-dependent reactions occur only when the plants are illuminated. Carbon assimilation or carbon fixation reactions, sometimes misleadingly called the dark reactions, which are driven by products of the light reactions. Photosynthesis takes place in the chloroplast. This is nothing but the same thing which is shown that NADP is NADPH plus H plus is generated and ATP is generated, which is then used in the dark reaction. Chloroplast structure. Okay, you must be knowing the theory that chloroplast and mitochondria were initially separate entities. Because of the endosymbiotic relation with eukaryotes, they became organelles. You know that they were prokaryotes which have chlorophyll in them. Okay, they made an endosymbiotic association with eukaryotes. Endosymbiotic means they entered the cell and that interaction was beneficial. Okay, after say a period of few years, millions of years, they became an entity of the cell. Now they cannot live without. Now you have to isolate chloroplast. It is not going to survive on its own because some of its properties have been transferred to the nuclear genetic material. Chloroplast has its own DNA. It also has its machinery to make proteins. Okay, but some of its properties have been transferred to the cellular DNA. That's why now chloroplast cannot survive as a separate entity. Yeah, the structure. There are three membranes: outer membrane, inner membrane, and there is a thylakoid membrane. There are three spaces between the outer and the inner membrane. There is an intermembrane space. Next, inside the inner membrane, there is stroma, where the dark reaction enzymes are present in solution. Then you have thylakoids. Thylakoids are made up of grana which are stacked one above the other, and the internal membrane of the grana contain all the reaction centers, that is the chlorophyll, the light harvesting complex, and all those intermediates like theophytin, quinone, all this is present on the internal side of the thylakoid membrane. So basically the light reaction takes place in thylakoids and the dark reaction takes place in the stroma. Again, compartmentalization, okay, of work. So all the enzymes are present in stroma, reaction center, light harvesting complex, etc. is present in the grana. That too, they are attached to the membrane, not free in solution. There is a reason for that also, we'll see. And inside the thylakoid, this space is the thylakoid space, which is called as the lumen. Okay. Light drives the electron flow in chloroplast. This is the famous Hill experiment. In 1937, Robert Hill, he conducted an experiment. What he did was he isolated chloroplasts, suspended them in water and gave light. He added an electron acceptor which is this 2,6-dichloro phenol indophenol. It is essentially colorless, blue in color, and when it accepts an electron, it becomes colorless. So when he provided light to these isolated chloroplasts, he observed that oxygen was evolved and the blue color was converted and it was colorless now. That means that there is some compound, this compound he added, this is not a natural compound. But with this he could deduce that there is some compound naturally present which accepts electrons. Later on it was found by Severo Opa that NADP is the naturally present electron acceptor. Okay, there was another experiment to determine where oxygen comes from. Okay, CO2, H2O, the initial reactants, both have oxygen. It is easy to think that CO2 can give oxygen, right? Gases. It is not the case. The oxygen comes from water, splitting of water. How was this proved? By using radioactive isotope of oxygen. First what he did was, CO2 that was used was labeled, that oxygen was labeled with 18, O18, the heavy isotope. And he observed the products where the radioactivity was coming from. The radioactivity was coming from glucose, not from the oxygen which was liberated. In second set, he labeled the water, H2O, that O was labeled with 18. Okay, and in the products, he tried to see where that radioactivity is coming from. And in this case, the radioactivity is coming from oxygen, not from the sugar which was produced. What does this mean? That the oxygen which is evolved comes from water, not from carbon dioxide. The splitting of water, what we call now. Now we move on to the light reactions. Light reactions essentially need a reaction center and a light harvesting complex. Now, the reaction center is usually chlorophyll A. Okay, you have chlorophyll. We will come to the structure of chlorophyll, xanthophyll, and all that. Now, light harvesting complexes are not the main center for absorption of light or photons. Their main function is transferring the energy of the photon to the reaction center, which is chlorophyll A. Now, this is just an example that this light harvesting complex is a trimer with 36 chlorophyll and 6 lutein molecules. Lutein is nothing but xanthophyll. Carotenoids are made up of carotenes and xanthophyll. Lutein is nothing but xanthophyll molecule. Now, 36 and 6. So, if it's a trimer, you divide it by 3. You get 12 and 6 divided by 3, 2. Okay, so 12 chlorophyll molecules and 2 xanthophyll molecules in one light harvesting complex. That is what is written down. 3 transmembrane helical segments, 7 chlorophyll A molecules, 5 chlorophyll B. 7 plus 5, 12. So we have 12 chlorophyll molecules and 2 molecules of accessory pigment, the lutein. Okay. So if it's a trimer, you multiply it by 3. So you get 36 and 6. The pigment of light harvesting complex. This is the chlorophyll structure. General structure, if you change this methyl group with an CHO aldehyde, you can convert chlorophyll A to chlorophyll B. That is the only difference between A and B. If you change this to a COCH3 structure, you get bacteriochlorophyll. What is bacteriochlorophyll? Chlorophyll present in bacteria. Even bacteria can photosynthesize, not all. Some of them which have this bacteriochlorophyll. Okay, again the saturated bond in bacteriochlorophyll, and that long chain is a phytol chain, which is a hydrophobic chain. Okay. Structure of phycoerythrobinin, beta-carotene, and lutein or xanthophyll. Okay. Now, in all these structures, you might have seen something common, that is alternating single and double bonds. Okay. Double, single, double, single, double. Okay. Even in these, we have alternating single and double bonds. What is the importance of these single and alternating single and double bonds? Absorption of light. Okay. Aromatic amino acids: phenylalanine, tyrosine, and tryptophan. You know the structure? They have a phenyl ring. उसमें थोड़ा modifications रहेगा. Okay. But they can absorb among all the 20 amino acids. Only these three can absorb. Right? You can determine proteins using these three amino acids. Why is that? Because you have this structure. Right? Now, this is green in color. Why do you see it as green in color?
Because
Yeah, I know, I just remember. It reflects green color, it absorbs rest all the colors. White light is made up of all 7 colors. It absorbs everything, only reflects green light. Why it absorbs all the other colors? Dyes are essentially benzene ring with many modifications. Okay, in that also you have alternating single and double bonds. Now, the advantage of having single double bonds is delocalization of electrons is possible. What is delocalization? What is localization? Localization means electrons are fixed. Now, just don't think of this. This is one bond. Okay. Now, your electrons are fixed between these two atoms, right? These two are carbon atoms. Electrons are fixed. What is the advantage with this? I'm sorry, how do you do this? Chat?
Chat.
Okay. I forgot this is an online class. Okay, so you can see there are alternating single and double bonds. In this, delocalization is possible. What is delocalization? These pi electrons can move here. These pi electrons can move here. So they are delocalized. That means they can move around. That's why you show when you draw benzene, you draw a circle in between, right? What does that mean? The electrons are not fixed. They can move. This is the property why some compounds can absorb, some others cannot absorb. Okay. Cyanobacteria and red algae. Okay, they have a different pigment system. Not your chlorophyll A, chlorophyll B. Not these are not the light harvesting systems. They have phycobilin pigments. Phycoerythrin, phycocyanin. Erythro, which color? Red. Cyanin, which color? Blue. Right? Cyan, magenta, red. Okay, and so these are colored pigments. They give the color to what you see. Red algae is, you will see red in color. It's because of these pigments that you can see the color. Now, these are the light harvesting system. What will the light harvesting system do? It will collect light, transfer it to other light harvesting system components. Finally, it will give to the reaction center. Okay? The reaction center is the one which is going to further pass it to the other molecules, but their function is only to transfer the energy of the photon from your sun, get it from the sun and transfer it to the reaction center. The energy of photons absorbed by phycoerythrin or phycocyanin is conveyed through an allophycocyanin AP phycocyanobacterin binding protein to chlorophyll A of the reaction center by exciton transfer. Exciton transfer is nothing but the excess of energy which is transferred to the next molecule. It's nothing but the same thing. Antenna, their light harvesting complex is also consists of antenna molecules. Antenna molecules, what does antenna do? It takes senses from your surroundings, right? It's the same thing. It picks up the energy from the surrounding, transfers it to the main reaction center, and the reaction center is going to carry out the further reactions. Okay. Now, why do you need such a wide variety of accessory pigments, chlorophylls, carotenoids? In that you need carotene, xanthophyll. Why such a wide variety? Because chlorophyll A has only 2 lambda max. Okay, at only 2 wavelengths, it's going to absorb maximum. Same thing with chlorophyll B. Okay, even carotenoids will have their own lambda max, the wavelength at which it's going to absorb maximum. Okay, so if the plant has to capture maximum amount of sunlight over a wide range of nanometers, visible is from 400 to 800 approximately, right? Right? Visible range is from 400 nanometers to 800 nanometers. But if lambda max is only at 465 and say 585, will it be efficient? No, right? You need molecules which will absorb over the entire range. That's why you have such a wide variety of chlorophyll, carotenoid pigments. Okay, and because there are many in number, each of them will absorb some energy of the photon, and all of them will transfer it basically to the reaction center.
But particularly colored pigment is present in only one organism. Chlorophyll is present in plants. Okay, those blue colored pigments now they are in bacteria.
Yeah. Your green plants, okay, your leaf is green in color, does not mean that it does not have carotenoid. Okay, it has carotenoids. Carotenoids are usually yellow, orange in color. What happens when the in autumn and spring? Yes, in India we don't have autumn and spring. Foreign countries, you might have seen in some movies or something, the leaves turn say yellow or brown in color. During that time, the chlorophyll goes down. Your other pigments are present. They start showing their color. But you are right. In your cyanobacteria or the ones which say red algae, these pigments are more. The other pigments are also present. Okay, the pigment which is present in majority is going to mask the other pigments. Like chlorophyll is present in majority, it is going to mask carotenoid. So you will not see yellow color. That means that the other pigments are present. The majority pigment marks the activity of the other pigments. Again the same thing. This is your reaction center, chlorophyll A. These are nothing but your antenna molecules. So this will take up the energy of the photon, transfer it to the neighboring antenna molecules till the energy reaches your chlorophyll A or the reaction center. Okay. Antenna, reaction center. In this also, this is your chlorophyll A molecule. Okay, these are the next molecules which come in the reaction, which we'll see later. But just remember that this one is your chlorophyll A. Now, light comes, it excites the first molecule, antenna molecule. What do you mean by excitation? Electron jumps to a higher energy level. You can see, now this has gone up, it's become excited. In the next step, it's excited, it will come back to its ground state. But what happens when it comes to the ground state? The energy that is had is going to pass on to the next neighboring molecule, which is this. So when this comes back to the ground state, this goes to the excited state. In the next step, since this one is closest to the reaction center, now this is going to transfer its energy to the reaction center. Here it has come back to its ground state. In the earlier slide, your electron is still in the ground state in the reaction center. Here it has gone it has become excited. Now, you can see these two energy levels are pretty close to each other. Okay, the chlorophyll A has of the reaction center I'm talking about. Chlorophyll A of the reaction center has energy less than that of the antenna molecules. One reason why all the antenna molecules give their energy to the reaction center. Why? Because chlorophyll A itself has low energy. When it gets energy, it completely throws out the electron. Okay, in that case, it becomes positively charged and the electron is lost. Electron taken up by the next molecule which comes in line. Okay, this is the process of photosynthesis in bacteria. We have P680 and P700, right? P700 is photosystem 1, P680 is photosystem 2. Bacteria, slightly different. They have P840 and 870. P stands for what? Pigment. Okay. The numbers stand for what? 840, 870. Nanometer. The wavelength of the light at which it will absorb maximum, right? So they have wavelengths 840 and 870. You'll see, this is the reaction. There are two examples are taken, purple bacteria and green sulfur bacteria. First we'll see purple bacteria is RC-P870. RC is reaction center and P870. Okay. First it receives excitons or it gets excited with photons. Gets excited, gives its electron to PO. PO is what? PO phytin. Next comes, next comes cytochrome BC1 complex, cytochrome C2, and it comes back to the reaction center. This is a cyclic process. Okay. This we'll see later that cytochrome BC1 forms a proton gradient due to which ATP is generated. You might remember while studying in 12th standard or something, we always used to write that it is that cytochrome B6F state, when the electrons come, ATP is generated. Why? We'll see study in detail later. But just remember that cytochrome BC1 is the location at which your ATP will be generated. Now this is green sulfur bacteria. RC-P840 is the reaction center. Excited by photons, gets excited. Now it has two fates. It can go a cyclic reaction or it cannot go a cyclic reaction, a non-cyclic reaction. Cyclic means it will go to quinone, it will go to cytochrome BC1 complex and cytochrome C553. And again at cytochrome BC1 we have a proton gradient and ATP is generated. If it is non-cyclic, it will go to pyridoxine. FD is pyridoxine. FNR, pyridoxine NAD reductase. The name only says it is going to reduce. Okay, so NAD gets reduced to NADH. Right, it's accepted the hydrogen and it has got reduced. If you remember the intermediates in your vascular plants, that means I'm talking about P680 and P700. Don't you think this is similar to P680 and this is similar to P700? Do you remember what comes in? Okay. Okay, what factor decides whether it is cyclic or not? Normally, it happens by a non-cyclic process. Okay, the assimilatory power is what? ATP and NADPH2. Right? This is the assimilatory power which is going to be used in the dark reactions. The cell requires or needs to make a specific ratio of ATP to NADPH2. What is that ratio? 3:2. The cell needs to make 3 ATP in the ratio to 2 NADPH2. Okay? If it has to fine tune this ratio, it requires both the presence of cyclic and non-cyclic. Non-cyclic is the one which normally occurs. Cyclic will occur only when it has to fine-tune the concentrations of ATP and NADPH2. Okay, what happens in cyclic? You know what happens in cyclic? The electrons come back from the photosystem which has started. P700. Next is ferredoxin. Then it goes to cytochrome B6, cytochrome F, plastocyanin comes back to P700. In this entire process, ATP is generated, NADPH2 is not generated because it is cyclic, not non-cyclic. Okay. In that case, the cells, the plant cell, will switch itself between cyclic and non-cyclic only when it has to fine-tune or regulate the concentration of ATP and NADPH2. Okay? Understanding? Okay. Fine. You know what? We'll see this. I'll just skip up. This is what happens in vascular plants. That I had shown you was in bacteria, right? This is what happens in vascular plants. You can see some of the components are similar. In that pheophytin was there, yes? In that quinone was there. Here you have PQ and PQA, PQB. But there quinone was there. There is cytochrome BC, right? Here this is cytochrome B6F. In this case also, ferredoxin was there, okay? And here, FNOR, that is ferredoxin NADP plus oxidoreductase. These are similar components. That's why we can say that at those billions and millions of years ago, when purple bacteria and green sulfur bacteria had evolved, okay? After that, the evolution was such that these two separate processes were combined together to make modern day vascular plants. You're understanding? This is the evolution. So initially that process was there, and during evolution it was found that this combining these two processes is more beneficial to the vascular plant. That's why today in modern vascular plants you have this non-cyclic process. Now, if your chloroplast, it takes energy from the photons, these energy can dissipate in the form of heat, right? If something has taken up energy, the easiest way to give out that energy is heat. Even our body, when we do work, the cells give out heat energy. Now, why after taking up the photon energy, it is not dissipated as heat? Because in the internal lining of thylakoids, you have these light harvesting system, the reaction center. All these are placed at strategic places, okay, so that the electron transfer is quick, the energy transfer is quick. If they are placed close to each other, right? If this gets excited and comes back to its ground state, if this is in close proximity, only then this will be able to take up the energy, right? If they are not present close to each other, if they are present in solution very far away from each other, they are floating in solution, right? If then one molecule gets excited and comes back, will the other molecule be able to take that energy? No. Why? Because they are far apart from each other. But because they are arranged in the internal lining of the thylakoid membrane and they are placed strategically, that means they are placed close to each other. That's why the energy is not dissipated as heat. It is transferred to the next component which comes in line. Standard free energy change is negative. Gives free energy. You know, right? If it's positive, it is not a spontaneous reaction. It has to be negative for the reaction to be spontaneous. Your gives free energy is minus 180 kilojoules per mole. This has been calculated, and because it is a negative value and a large negative value, the reaction occurs spontaneously. Now, this is what happens in normal eukaryotic vascular plants. You can't see this properly. You have the first is P680. Okay, P680 is PS2, photosystem 2. P700 is photosystem 1. When PS1 gets the photons, so the light energy gets excited, A0 and A1 are nothing but slight modifications of chlorophyll molecules. From there, the electron transfers, goes to FeS, iron, sulfur, ferredoxin, FD-NADP, oxido, reductase, and because this is reductase, it converts NADP to NADPH. Okay? Your P680 gets excited, goes to the electrons goes to pheophytin, PQA, PQB. It will go to cytochrome B6F complex, plastocyanin. This was deficient in electrons, right? It received photons, it gave the electrons, but it never got electrons back. Plastocyanin is the one which will give the electrons to P700. Now you will ask, P680 is also deficient in electrons. Where does it get its electrons from? Splitting of water molecules. Okay, water is split into H plus, 4 electrons, and oxygen is given out. Those 4 electrons neutralize your P680. Okay, this is complicated. This is G1 and D2 transmembrane protein in which your entire complex is situated. What is it? This?
What happened? The electron is coming from ferrous sulfate to cytochrome B6.
Okay, no. This is the non-cyclic. What I explained to you was non-cyclic. This is a cyclic process. They have just combined the two together. In cyclic, what happens? P680 never participates. It's only P700. Okay, P700 gets excited, goes to ferredoxin. It does not form NADP and NADPH2. Ferredoxin gives the electrons to cytochrome B6F, plastocyanin, and P700 gets its electrons back. Okay, because the starting point of the electron is the same as the end point of the electron, the process is called as a cyclic process.
Both the photosystems, which one is receiving first light reaction is happening here and there. Which one is the initial one? First P700 is excited?
First P700 one is excited. To neutralize that P700, this takes and the plastocyanin donates its electrons to P700. P680 now is deficient in electrons. To neutralize P680, water splits. This reaction is continuous. Okay, nowhere it is stopping. What is another use of water splitting? This NADP has to be reduced to NADPH plus H plus. So you have to add H and H plus. Where does that H plus comes from? It comes from splitting of water molecule. Okay, and that H plus combines with NADP and reduces it to NADPH. Electrons neutralize your P680 and oxygen is liberated, right? That's why plants take in carbon dioxide and give out oxygen. Okay, the membrane complex in which your reaction center, light harvesting complex, everything is present. Now the first point is P680, the starting point. P680 gives the electrons to pheophytin. Pheophytin gives it to PQA, plastoquinone A. Third, they have shown it over here. P680, okay? Just now I told you that water is the one which will give its electrons to neutralize P680. This transfer is not direct, it is indirect. To neutralize P680, tyrosine will give the electrons. To neutralize tyrosine, magnesium, so manganese, okay, which is Mn0 in valency, will give 4 electrons to tyrosine and become Mn4 plus. Manganese can have valency 2, can have valency 4, and can have valency 7 also. It will give 4 electrons to tyrosine, and this will get neutralized with the help of water, splitting of water. That is what I meant, that the transfer of neutralization of P680 is not a direct process. It happens because of splitting of water. Okay, but it will occur via the way of manganese and tyrosine. Okay. Now, after phytoquinone A, it goes to the electron goes to phytoquinone B, and PQBH2 is formed on the membrane. Okay, this PQBH2 gives it to cytochrome B6F, gives it to plastocyanin and photosystem 1. That means P700. When plastocyanin gives it to P700, it goes to, there are many molecules. These are intermediate stages, after which it comes to pyridoxine, NAD oxidoreductase, NADP gets converted to NADPH+, H+. Okay. Remember, in non-cyclic process, both ATP and NADPH+, H+ are formed. In cyclic, only ATP is formed, NADPH+, H+ is not formed because this enzyme is not occurring in cyclic. After pyridoxine, it directly goes to cytochrome B6, cytochrome F, plastocyanin, and it comes back to the original point. There is no enzyme. That's why NADP is not reduced. Okay. So overall reaction, whenever the electron comes to cytochrome B6F, I will tell you how. So just okay. Passage of electron system. Okay. Which is where is the starting point of the electron? It's P680, right? Receives photons, gets excited, throws out an electron. First to capture that electron is thiophytin. Thiophytin will give it to plastocyanine A. Okay? Plastocyanine will give it to plastocyanine B, and it will form PQBH2. Now we will ask me where this H2 comes from. It has received an electron. Okay? Loss of electron is oxidation. Gain of electron is reduction. So PQB, when it receives electron, it gets reduced. It also combines with an H+. Okay? It combines with H+ and forms PQBH2. Where does it pick this H+ from? It picks the H+ from the stroma. This entire part is the lumen, this part is the lumen side, this is the membrane, this is the stroma. Okay, where the enzymes are present. It picks up hydrogen from the stroma side. When it donates the electron to cytochrome B6F, it gives the hydrogen into the lumen side. Okay, that's why in the lumen their hydrogen concentration is more. pH is always less in the lumen as compared to the stroma. The electron then is transferred from cytochrome B6 to plastocyanin, and then it goes to photosystem 1, which is P700. Okay. Now, from plastocyanin, it has come to P700. With all these intermediates, it goes to pyridoxine, FNOR, pyridoxine NADP oxidoreductase, and finally forms NADPH+, H+. Okay? Any confusion with this? So overall reaction of photosynthesis: water, NADP. NADP is getting reduced to NADPH plus H plus. Okay, water is being oxidized to oxygen. 4 electrons are required to make one molecule of O2. How? H2O has just one oxygen. Okay. When it splits, you have to make one molecule. You need 2 H2O. When 2 H2O splits, you get 2 H plus. 4 H plus, 4 electrons and oxygen. Okay. That is why it is said that 4 electrons transfer makes one molecule of oxygen. Now, prevention of excitant larceny under the excitation of PS2. Excitation larceny, this I have to explain you with this. I just repeated, no? Okay. In this, what I forgot to tell you was how P680 receives its electrons back. What I had told you, for P680 to get its electrons back, water has to be split. Okay, that process is going to neutralize the P680, excited P680. But this transfer is not direct. So water is not directly going to split and the electrons are not directly going to come and join P680 to neutralize it. What happens is, when P680 first becomes positively charged, that means it gives its electron away, tyrosine is placed very close to it. It will give its electrons to P680 and neutralize it. Now tyrosine is in need of electrons, right? Who will give the electrons to tyrosine? It is this manganese ion which will give the electron to tyrosine. Itself it will become oxidized. That means its oxidization state goes on increasing. When it gives 1 electron, it becomes Mn plus 1. Gives 2, it becomes Mn plus 2. Like that it gives 4 electrons and becomes Mn plus 4. So it gives the electrons to tyrosine. And where does this get neutralized from? By splitting of the water molecules. So water will split, it will generate 4 electrons, that will go and neutralize your Mn plus 4. So Mn plus 4 electrons will become a neutralized manganese with a 0 valency. So everything back to normal, happy and happy. Now the next step will be again when P60 gets photons, it will again become excited and go to the entire process now continues as it is. Okay, exciton larceny. Okay, for this. Now, what is on the y-axis? It is electron volts. Okay. Now you can see this P680 is approximately at 1 electron volt. P700 is approximately at 0.5 electron volt. That means which has less energy? P680 or P700? P680 is at 1 electron volt. See, this is the energy. Okay. E dash naught is standard free energy. P680 is at 1 electron volts and P700 is at 0.5 volt. So, if you give 0.5 volts to this chloroplast, which will get first excited? 700. See, for P680, you need to give 1 volt of energy. For P700, you need to give 0.5. Okay, so if both of these are present in combination with the chloroplast, you give 0.5 volts. P700 is the one first to get excited. Now the problem with these two sitting together in the chloroplast is that P700 will always get excited first as compared to P680. Why? Because its energy is less. Okay, it happens so that always P700 will be the one which is excited, P680 will be under excited. That means only this part of the reaction will be completed, the right hand side. This will stall. It will happen, then it will stop again. It will happen, then it will stop again. It will not be a continuous process. Why? Because P700 has less energy. It will take up the energy of the photons. To prevent this, the two photosystems are separate or they are compartmentalized. P700 is present at a different place, P680 is present at a different place. If that is the case, then if you apply that energy near P680, now P700 is not there and P680 can now perform its functions efficiently. Why? Because P700 is not there to take P680's share of energy. This is exciton larceny. Prevention of exciton larceny under excitation of PS2. If PS1 is closely present next to PS2, PS2 will always be under excited because it has higher energy level. PS1, photosystem 1 and ATP synthase, they are present separate. Photosystem 2 is placed separate. Photosystem 2 is the one which has higher energy, right? 680. Therefore, it is placed separate. Now, this is appressed region. This they are called as non-appressed or unstacked membranes. Appressed means what the name says. Appressed means they are placed very close to each other. These two are pressed. That means appressed. Here they are not very close. They are a little at a distance. Even this is at a little distance. That means they are unappressed. Now, unstacked membranes or stromal lamellae. Now there are two lamellae, granule lamellae and stromal lamellae. If you remember the structure of thylakoids, there are stacks of grana. Between two thylakoids, there was a connecting link which is lamellae. That is your stromal lamellae. You can see this, if this extends ahead, there will be another stack of grana. Okay, this is your stromal lamellae. And this is your granule lamellae. Between two stacking, there will be some space. That is your granule lamellae. So stromal lamellae is unappressed. They are a little distance from each other. Whereas granule lamellae are appressed. They are very close to each other. And in granule lamellae, you only have PS2. P680 is separate from the other two, whereas in the stromal lamellae, you have PS1 and ATP synthase. Now, because of this physical separation, your exciton larceny does not occur. Under excitation of PS2 does not occur. Again, the same thing. This is appressed, pressed. Non-appressed, they are separate from each other. Why does this occur? This is light harvesting complex has a threonine residue with an attached hydroxyl group. Now, due to this enzyme, protein kinase, it gets phosphorylated. Because of phosphorylation, the two membranes, they go a little far apart from each other. If you think logically, phosphate is a very huge group as compared to an OH, right? Because of this, they get separated and you can interconvert between appressed and non-appressed regions. This is again the water splitting activity shown in a different way. Okay, this is that tyrosine residue which was next to P680, and the tyrosine was in contact with the manganese ion, Mn ion. Now, water, when P680 gets excited, these are all photons that are exciting P680. Tyrosine is the one which will neutralize P680. You can see at every stage, the manganese is losing one electron. It is giving it the electron to tyrosine so that tyrosine gets neutralized. And what about this Mn? It is neutralized by splitting of water. So at the end of it, you have oxygen which is given out, released, and you have 4 hydrogens which are released into the lumen. That is why I said lumen is more acidic. It has more H plus ion concentration as compared to the stroma. Why am I telling you this again and again? Because this pH gradient, difference in the pH, is the one which is responsible for generation of ATP. Cytochrome B6F, we are coming to that now. This is the lumen, called lumen. Here H plus is more. Okay? If H plus here is more and in the stroma it is less, a pH gradient is formed. Gradient is what? At one place is more, at the other place it is less. In that case, this is your ATP synthase enzyme. Okay? This enzyme functions when it throws a hydrogen out. It combines the throwing of hydrogen ion out to the process of generation of ATP. Okay, the energy which is involved in throwing the hydrogen out is used to make combine ADP and PI to form an ATP. Okay, and this is in conjunction with cytochrome B6F. Cytochrome from plastoquinone PQHB2 to cytochrome B6F, from cytochrome B6F to plastocyanine. During this entire transfer of electron, because of this transfer of electron, this hydrogen is thrown out by ATP synthase, and because of this throwing out of hydrogen, here ADP plus PI combine to form ATP. Okay, what if this hydrogen gradient, pH gradient would not have been there, then the ATP would not have been synthesized. But that is the main aim, right? ATP synthesis is the main aim of the process. Okay, this is the energy. You have a proton motive force or a proton gradient is generated. This is the formula delta G 2.3 RT gas constant temperature. Delta pH is the difference in the pH in the lumen and the stroma outside. Z is the charge on the molecule. F is the Faraday's constant, and delta psi is the electrical potential due to charge separation. The movement of 12 moles of protons across the thylakoid membrane represents conversion of about 200 kilojoules of energy, enough energy to drive the synthesis of several molecules of ATP. That is what is being said. Okay, how 12 protons are produced per oxygen molecule. Now, remember I told you 4 electrons are required for generation of one oxygen molecule. That along with the 4 electrons, 4 hydrogens. This. How many hydrogens are there? 4. This hydrogen is pumped into the lumen by this process of splitting of water molecule. And cytochrome B6F throws the additional 8 electrons when it is transferring the electrons from plastoquinone PQBH2 to plastocyanin. PQBH2 loses its hydrogen, yes or no, to be converted into PQB. That 2 hydrogen, if you multiply, 4 electrons are getting transferred. So 4 molecules of PQBH2 will be converted to 4 molecules of PQB. So kitna hydrogen? How many hydrogens are gone? 4 into 2, 8. So these 4 plus those 8 hydrogen, how many? 12. Right? You understood the split up? If you not understood, which one?
The chain we have done, PQB.
One second. Are they shown here? Just one second. PQB. Yes, this one. Okay. Now this PQBH2. PQB receives electrons from PQA. Okay, and it takes up hydrogen to form PQBH. So basically, PQB is getting reduced to PQBH2. When PQBH2 transfers its electrons to cytochrome B6, it will give away its hydrogen also. If 4 electrons are being transferred, right, one after the other, that means 4 times PQBH2 is going to give the hydrogen away. One time it gives 2 hydrogen. 4 times it will give 8 hydrogen. These 8 hydrogen plus the 4 hydrogen which is obtained from splitting of water molecules. So total 12 hydrogens are generated at one time is thrown out into the lumen. I hope Parul you have understood. Okay, 12 moles of protons across the thylakoid membrane represent conservation of about 200 kilojoules of energy, enough to drive the synthesis of ATP. That means this throwing of protons from the stroma into the lumen generates a proton gradient or a proton motive force, because of which your ATP synthase can synthesize ATP. The experimental measurements yield values of about 3 ATP per oxygen molecule. Now this 3 ATP, I cannot show you where ATP is generated. This value of 3 ATP has come from experimental results. Okay, they have conducted a lot of experiments and now they have come to the conclusion that approximately for 1 molecule of oxygen, 3 molecules of ATP are generated. This you have to remember. This nobody can account for. At this step, 1 ATP is generated. Not like that. This is what they have found experimentally, that for 1 molecule of oxygen, 3 molecules of ATP are generated. Comparison of the topology of proton movement and ATP synthesis orientation of membrane of mitochondria, chloroplast, bacteria.
Time is over. Conclude first.
2 slides left, and I'll finish it. Okay. Okay. This ATP synthesis also occurs in along with chloroplast, it occurs in mitochondria and the membrane of the bacteria. The overall process is the same, that a proton gradient is generated and ATP synthase, because of this proton gradient, generates an ATP. The only difference is the location at which the hydrogen is more in concentration and less in concentration. See, the mitochondria is again a double layered structure, right? Double membrane. The inner membrane has many invaginations, which is called as cristae. Now, inside it is matrix, and this is the intermembrane space, that is between the inner membrane and the outer membrane. So, in this is the intermembrane space and the matrix. So, in the inner membrane, you have your ATP synthase. H plus is taken from the matrix into intermembrane space. So here protons will be more, pH will be less. Okay, because then this ATP will combine and form ATP when it throws the hydrogen from the intermembrane space into the matrix. Now chloroplast we have already studied. The flow is from lumen. In lumen it is more, H plus is more, and it throws it, the ATP pump throws it out in the stroma side. What happens in cytosol? This is a bacteria. Cytosol, and this is again a membrane. This is the intermembrane space, and cytosol. In the intermembrane space again, H plus is more, similar to your mitochondria. It will throw the protons outside, and here ATP is generated, which the bacteria uses for its purposes, say movement or something. Now, probably the last slide. Energy yield of non-cyclic photophosphorylation. Same reaction, I have just shortened it. 2 water, 8 photons. Okay. 2 NADP, they get converted to NADPH plus H plus. I told you approximately 3 ATP are generated. And energy yield of, this is non-cyclic. In non-cyclic, NADPH plus H plus is also generated. In cyclic, you can see only ATP is generated, not NADPH and H plus. Okay. This is the half of the topic I have completed. So next time I would try to complete it with the remaining dark reactions. Any doubts?
Which book?
This is a combination of Leninger and Lodish, cell molecular biology.
Next.
Oh, okay.
There's only one ATP produced in
In cyclic, when it gets converted from cytochrome B6, there is again cytochrome B6. So that one ATP is generated at that process. If the cyclic process takes place continuously, the number of cycles will give you the number of ATP which is generated. Okay, first one is Leninger, the other is Lodish, Lodish, cell molecular biology.
If both the processes are going on, then 4 ATPs are produced. One from the cyclic and
the other one from the non-cyclic. But this is what I told you. When will the cell turn on its cyclic photophosphorylation? When it has to fine tune, when it has to regulate the concentration of ATP and NADPH2. For the later reactions, dark reaction, it requires ATP and NADPH2 in the ratio of 3:2. Okay, if the ATP concentration is low, okay, for the dark reactions to occur, then what it will do? It will activate the cyclic photophosphorylation. In that case, what will happen? Only ATP will be generated, not NADPH2. Okay, in that case, ATP concentration will increase. So this cyclic phosphorylation is only present to fine tune or regulate the number of ATP and NADPH2. I hope this is clear to all of you. Any doubts? Any more doubts? Doubts?
Is it important to remember all the structure of flow
I suggest you remember what is the difference between the structures. Bacterial chlorophyll mein, there was COCH3. In between chlorophyll A and B, what was the difference? CH3, a methyl group in chlorophyll A, and there was a CHO, an aldehyde group in chlorophyll B. If you cannot remember the whole structure, we have studied it in BSc and MSc, but it is slightly difficult to remember. At least you should remember there is a porphyrin ring structure. Okay, there is an extra 5-ring membered group in chlorophyll. Chlorophyll is similar in structure to cytochrome hemoglobin because even they are porphyrin ring structures. The difference is over here, what is there as the cofactor? Magnesium ion. Mg. Mn chlorophyll. Chlorophyll has magnesium. Hemoglobin will have ion. Cytochrome will have ion. These are the things that you should remember. Even phytol, side chain. No.
And what kind of questions are asked from this portion?
From this entire thing, they will mainly play with the number of what is what generated. Say now in this, I just give an example. How many photons are required for one one oxygen? This is one example. Other type is the next reaction. Okay, dark reaction. In that you have C3, C4, CAM. Okay. In that there was one question which was just asked last time. What happens when the temperature increases? Okay, this I'll teach you the next time. What happens when the temperature increases? C3 is better, C4 is better. CAM mein kya hota hai? All this. Okay, but you have a good chunk of questions from this. Okay.
Part B or part C?
This is part B. The examples that I told you was part B. Another one was the enzyme Rubisco. Just last June, I gave the paper, which is the most abundant protein on Earth. The options were Rubisco, cellulose, and 2 others. The 2 others were not you know, you can just look at them and say that no, this is not the option. Usually people get confused between cellulose and rubisco. Why cellulose? Cellulose is a structural component of plant. You think that cellulose can be more in concentration. Why? Because you have abundant plants on the earth. Okay, that is not the answer. Rubisco is the answer. This is what I am trying to tell you, that these type of questions can come. So what I am going to do is, every time you know, the question has been you know, something related to the question comes, I just mention it to you that okay, this, you know, that question was asked when C3, C4 comes, when rubisco comes. Okay, I give you the reason for the same, why rubisco is abundant. If you need any help, just contact me. Thank you. Oh, what's the time? Okay, the class is till 5:30.